to the deep dive. Today, we're going to take on probably the most fundamental assumption you have about the universe.
Oh, this is a big one.
It is. It's an assumption that's, baked into your everyday experience. And we're going to argue that it's likely a beautifully persuasive illusion.
You're talking about volume, right? The idea that things have depth.
Exactly. We're challenging the very idea that volume matters.
It's the intuition we use for everything, isn't it? I mean, you want to store more stuff, you get a bigger box. You want more data, you buy a bigger hard drive.
Right. In classical physics, capacity, whether you're talking about atoms or information, it scales with volume. That's proportional to the radius cubed.
That whole volumetric intuition. It's the bedrock of how we think about three-dimensional space.
But the radical, truly world-upending conclusion of modern theoretical physics is that this intuition is just fundamentally wrong.
Yeah, the complexity, the sheer amount of information you can pack into any region of space.
Yeah.
It's not actually stored in the volume.
Which is so hard to get your head around.
It is. We've moved into a scientific paradigm where the depth, the bulk space-time we all live in, complete with the force we call gravity, it's all understood to be a projection.
An emergent phenomenon.
Exactly. A statistical byproduct of something far simpler and much more fundamental happening on a distant boundary surface.
So our mission in this deep dive is to explore what you could call the computational architecture of reality.
Mm-hmm.
We're going to trace the intellectual path that led physicists to say, okay, the fundamental layer of reality is actually a lower dimensional quantum system. A screen, if you will.
And that screen is encoded with all the information needed to create the illusion of depth and even the feeling of gravity.
And we'll get into the mathematical proof that actually links a universe with gravity to one without it.
And my favorite part, how quantum entanglement literally becomes the glue, the very fabric that weaves space together.
And then there's this surprising hypothesis that our smooth, stable reality is basically being maintained by a kind of robust, self-healing, quantum error-correcting code.
Right.
So that brings us to the big question. If gravity isn't a fundamental force, but it's more of a statistical byproduct, like heat is the byproduct of molecules moving, then what is our reality?
And to answer that, you have to start where this whole crisis began.
With the one object in the universe that just smashes classical physics and quantum mechanics together.
To a black hole.
Let's start there.
So the road to this whole holographic principle, it really started with a crisis of entropy back in the 1970s.
Okay.
For decades, based on Einstein's general relativity, a black hole was considered the simplest, most featureless object possible.
This is the no-hair theorem, right?
That's the one. It's defined by only three things: its mass, its charge, and its spin. That's it.
And that term no hair really drives the point home. It's saying a black hole has no complexity, no memory of what it swallowed, just those three numbers.
It's perfect simplicity. But the problem starts the moment you bring thermodynamics into the picture.
Specifically the second law.
Right. The law that says the entropy or the disorder of a closed system has to always increase. It can never go down.
And entropy is really just a measure of information, isn't it? It's the number of ways you can sort of rearrange the microscopic bits of the system without changing how it looks on the outside.
Exactly. So think about a tank of hot, complex gas. Or even better, a hard drive filled with billions of unique bits of information. That's a very high entropy object.
Okay, so if I take that hard drive and I throw it into a black hole.
All that information, and therefore all that entropy, it should just vanish from our observable universe.
Because the black hole itself has no hair. It has no internal complexity to store that information.
And if the entropy just vanishes, the second law is brutally violated.
Which would be a disaster for physics.
A total disaster. You could
go.
basically build a perpetual motion machine or even reverse the flow of time just by erasing complexity. It was a contradiction that just couldn't stand.
And this is where Jacob Bekenstein comes in.
Yes. He recognized that to save the second law, the black hole must have entropy. It can't just be a gravitational void. It has to be the ultimate information storage device.
It has to hold on to the complexity of everything that fell into it.
It has to. And this is where his solution completely flipped that volumetric intuition on its head.
How so?
Well, if the black hole's entropy had scaled with its volume, with R cubed, nobody would have blinked. It would have been a standard, boring mathematical solution.
But that's not what he found.
Not at all.
Yeah.
He found that the entropy didn't scale with the volume. It's scaled precisely with the surface area of the event horizon.
With r squared.
With r squared. So the information content of this huge three-dimensional interior was capped, completely determined by the size of its two-dimensional boundary.
That is so weird.
Think about what that means. A normal computer storage is limited by its volume, how many hard drives you can physically fit inside the case. Bekenstein was saying the universe's storage capacity is limited only by the square footage of the walls of the container, no matter how much empty space is inside. It just defied all common sense.
I can't imagine that idea was accepted easily. It connects gravity and information in such a radical way.
It was a huge career-risking claim. I mean, initially, even Stephen Hawking was deeply skeptical.
Oh, really?
Yeah. He argued that, well, if a black hole has entropy, it must have a temperature. And if it has a temperature, it must radiate energy. So it can't be perfectly black.
Which seems like a good argument against it.
It was. But in the process of trying to disprove Bekenstein, Hawking actually discovered something that confirmed it completely.
And that was Hawking radiation.
That was Hawking radiation.
Yeah.
He proved that due to quantum effects right at the edge of the horizon, black holes do, in fact, radiate a perfect thermal spectrum.
And the temperature of that radiation matched what Bekenstein's entropy predicted.
It matched it perfectly. And that confirmation led to the Bekenstein-Hawking entropy formula, which is, I mean, it's one of the most important equations in modern physics.
We should probably pause on that for a second because it really is the Rosetta Stone of quantum gravity. It connects 4 different pillars of physics in one statement.
You're absolutely right. I mean, just look at the constants in the formula. You have Boltzmann's constant, KB, that's the heart of thermodynamics.
Then you have C, the speed of light from special relativity.
You've got G, Newton's gravitational constant, which is the key to general relativity.
And crucially, you have P, Planck's constant, the fundamental scale of quantum mechanics.
To see G and Heg together in a single measurable quantity for the first time, it was monumental. There's a rigorous quantifiable statement that the macro world of gravity and the micro world of quantum mechanics are not just related.
They're inextricably linked.
Through the black hole horizon and through the concept of information.
So this led to a more general rule for the universe, not just for black holes.
It did, the Bekenstein bound. The idea is that the maximum information capacity of any region of space is not based on its volume, but on its surface area.
It's a universal speed limit on information density.
Exactly. And Bekenstein showed that if you try to pack more information into a region than its area allows,
let me guess, it collapses into a black hole.
the energy required to store that extra bit of data becomes so immense that the system has no choice. It must gravitationally collapse, forming a black hole, which then strictly enforces that area limit.
So gravity itself is the enforcement mechanism. It's the universe's way of preventing an information overload.
That's a perfect way to put it. Gravity is the universe's self-correcting defense system. And this leads directly to the formal statement of the holographic principle, first articulated by Gerard Tooft and later really championed by Leonard Susskind.
The idea being, if 3D capacity scales with 2D area, then our 3D description of the world must be, well, highly redundant.
Very redundant. The conclusion is that the fundamental degrees of freedom, the true bits of reality, they can't live throughout the volume. They have to live on the 2D boundary surface.
So our entire 3D experience depth, the smoothness of space, even gravity itself, is all just a holographic projection.
The volume is an illusion of depth generated by data on a surface. But, you know, for years, this was still just a powerful conjecture. It needed a concrete mathematical model.
A working example.
Exactly. A proof that this translation from 2D data to 3D geometry was actually possible.
And that proof arrived in 1997 from Juan Maldacena, his AD-SCFT correspondence.
Yes. And this wasn't just another hypothesis. This was a specific computable dictionary for holography, a proven equivalence.
Maldacena showed that a universe that contains quantum gravity is somehow exactly equivalent to a universe of quantum fields that has no gravity at all.
That's right. 2 totally distinct theories describing the exact same physics. It's a duality.
So let's break down the 2 sides because they sound completely incompatible. On the gravity side, the bulk theory, what are we looking at?
We're looking at type IIB superstring theory. It's a framework that tries to unify gravity and quantum mechanics by treating particles as tiny, vibrating strings.
And this theory is set in a specific kind of spacetime.
A very specific one. A 10-dimensional spacetime. It's 5 dimensions of something called anti-de Sitter space, or ADS, combined with 5 dimensions of a compact sphere. So 8s5 times s5 5.
And this is a universe with gravity.
Oh yes. At low energies, It approximates classical general relativity. It has gravity and depth.
Okay. And it's mirror image, the boundary theory without gravity.
That is something called Mathekal super Yang-Mills theory. Now, that's a mouthful, but Yang-Mills theory is just the mathematical structure we use for the fundamental forces.
Like quarks and gluons.
Like quarks and gluons. And this specific one is a conformal field theory, or CFT. It lives on the four-dimensional boundary of that ADS space, and crucially, it contains zero gravity.
So, to recap, a complex 10-dimensional string theory with gravity on one side, and a 4-dimensional particle field theory without gravity on the other. And you're saying they are mathematically the same thing.
Identical. Every particle, every interaction, every single thing you can measure in the string theory has a precise equivalent in the field theory.
That's the dictionary.
That's the dictionary. It suggests that the gravity and the extra dimensions in the bulk, they're just a convenient way of visualizing the very complex interactions happening between the quantum particles on the boundary.
You mentioned anti-de Sitter space, ADS. Why that specific geometry? Why is it so important for this duality to work?
It's because ADS space has a negative curvature. It's sort of saddle-shaped everywhere, unlike our universe, which is mostly flat or slightly positively curved.
And this negative curvature creates a sort of a universe in a box.
A perfect way to describe it. Think of it like a solid cylinder where time runs up the side. The boundary is the surface of the cylinder, and the interior is the bulk.
The geometry is hyperbolic, like in an M.C. Escher drawing.
Exactly like that. As you move toward the boundary, distances seem to shrink exponentially. This means that even though the boundary is technically at spatial infinity,
a beam of light can get there and back in a finite amount of time.
It can. The light ray goes out, hits the boundary, and reflects back in. The boundary acts like a perfect gravitational mirror, which creates this stable, fixed surface for the quantum field theory to live on.
And from that surface, it projects the gravitational physics into the interior.
Right. But the really practical and, frankly, amazing part of AD-SCFT is what's called the strong-weak coupling miracle.
This isn't just a pretty symmetry, it's a computational tool.
It's the ultimate computational tool. The two theories are linked by their coupling constants, which, just measure how strongly their particles interact.
And these constants are inversely related.
They're inversely related. So when the math on one side becomes impossibly difficult,
the math on the other side becomes easy.
Precisely. When the boundary CFT is strongly coupled, meaning its particles are interacting so furiously that your normal calculation methods completely break down, the dual gravity theory in the bulk becomes weak, large, and classical.
It simplifies down to Einstein's equations.
It simplifies to the relatively manageable classical Einstein equations just in 5 dimensions.
So you can use this to solve problems that were otherwise completely intractable. What's the classic example of this?
The classic example is calculating the viscosity of the quark-gluon plasma.
That's the stuff that filled the universe for the first few microseconds after the Big Bang.
The very same. It's an incredibly strongly coupled fluid, and we can make tiny droplets of it in particle accelerators. But trying to calculate its properties, like how sticky it is, using our standard theory of quarks and gluons, it's mathematically impossible.
But with the AD-SCFT loophole.
With the loophole, you just use the dictionary. You map the impossibly hard 4D quantum fluid problem onto a much simpler problem.
You treat it as a black hole in 5D ADS space.
You treat the quantum fluid like a black hole fluid. You solve the straightforward classical gravity equations for that 5D black hole, and the result it gives you for the viscosity.
It matches the experiments.
It's remarkably accurate. It's one of the strongest pieces of practical evidence we have.
That is just... It really implies that gravity isn't fundamental at all. It's an emergent statistical thing.
It's like hydrodynamics. You don't describe a tidal wave by tracking every single water molecule. You use fluid dynamics.
The emergent macroscopic description.
In the same way, gravity is the emergent macroscopic language we use to describe a vastly complicated underlying quantum information system. Spacetime is just the most efficient way to organize all that data.
Okay, so if spacetime is emerging from quantum data, we need to dig into that dictionary Maldacena gave us. How specifically do these quantum concepts on the boundary become concrete things like gravity and depth in the bulk?
Let's start with the most basic building blocks. In the dictionary, if you have a local excitation on the 4D boundary, what physicists call a field operator, that corresponds exactly to a fundamental field, like a particle, in the 5D bulk.
So a particle sitting inside the bulk is really just a ripple in a field that lives on the distant boundary.
That's it. And what about the force that governs them? Gravity itself.
How does that show up?
Well, gravity in the bulk is generated by the way energy and momentum are distributed on the boundary. That's described by something called the stress energy tensor.
So the energy flowing around on the boundary.
That manifests in the bulk as gravitons, the particles that carry the gravitational force and tell space-time how to curve.
The gravitational field we feel is a direct output of the energy of the non-gravitational system on the boundary. It's like the processing load of a giant computer is generating the geometry of its own display.
As a perfect analogy, the geometry is the output. But the really profound translation is about depth. How does this flat 4D boundary generate a fifth dimension that gives us this illusion of volume?
And this is the IRUV connection, right? The peeling of the onion.
Correct. The radial coordinate in the bulk, let's call it Z, maps directly to the energy scale of the physics happening on the boundary.
Okay, what does that mean?
Well, the boundary itself at Z equals 0 represents the highest energy, shortest distance physics, the ultraviolet or UV scale.
Like looking through a microscope at the finest possible detail? That's what's happening right on the screen.
Right. And as you move inward into the bulk, as Z gets larger, you are effectively zooming out. You're probing lower energy, longer distance physics on the boundary, the infrared or IR scale.
So the deep interior of the ADS space is where the macroscopic low energy physics live.
Exactly. The radial dimension, our sense of depth, is literally defined by the energy scale of the boundary theory. It's not a fundamental axis, it's a coordinate defined by how the information is organized.
Which has a huge implication for how we think about black holes.
A massive one. In the bulk, a black hole is this extreme gravitational object, a singularity.
But on the boundary, what is it in the dictionary?
On the boundary, a black hole in ADS is nothing more than a hot thermal state of the boundary quantum particles. It's a soup, a plasma of strongly interacting particles.
So the event of a black hole forming in the bulk
Corresponds precisely to a deconfinement phase transition in the boundary theory, the moment the plasma is born.
So you've transformed this impossible problem of quantum gravity near singularity
Into a solvable problem of statistical mechanics on a nice, flat, stable boundary. The black hole is just the thermal limit of the quantum system.
This keeps reinforcing that idea. Gravity is just the thermodynamics of the underlying quantum code.
It's the hydrodynamics.
Okay, so if the universe is a projection and gravity is a byproduct, what's the actual stuff that weaves it all together? Volume isn't real, but connections are. Things are next to each other. How does that happen?
The mechanism is quantum entanglement.
The spooky action at a distance.
That's the one. Entanglement is the glue. It's what constructs the geometric bulk and gives us our sense of connectivity and locality.
And this link was made mathematically concrete in 2006 by Ryu-Takayanagi, the RT formula.
Yes, the RT formula is profound. It states that the entanglement entropy of a region A on the boundary.
So a measure of how entangled that patch is with everything else.
Exactly. That quantity is directly proportional to the area of a minimal surface that hangs down from the edges of A into the bulk.
Like a soap bubble stretched across a wire loop, dipping down.
A perfect visual. And the equation itself is stunning. It says a quantity from information theory, entropy in bits, is equal to a quantity from geometry, area in meters squared, divided by the gravitational constant.
Information is geometry.
They are mutually definitional. You can't have one without the other. The amount of entanglement determines the geometric size of the cut you need to make in the bulk to separate that region.
And the shape of that soap bubble, that minimal surface, tells you something about depth.
It does. If you take a tiny little patch A on the boundary, its minimal surface is very shallow. It barely dips into the bulk. But as you make region bigger and bigger, the minimal surface has to plunge deeper and deeper into the ADS interior. It forms this big hammock that spans a huge distance in that fifth dimension.
So the very center of the bulk, the deepest part of the interior, it's not defined by some local coordinates.
No. It's defined by the maximal non-local entanglement shared across the entire boundary system. Our perception of here is a manifestation of dense quantum correlation over there.
It's really turning things inside out.
It is. And the RT formula is really a holographic generalization of the Bekenstein-Hawking formula for black holes. The event horizon is just the minimal surface that separates what we can see from what we can't.
So if entanglement creates the connection, then getting rid of entanglement should destroy the connection.
Exactly. And this led to a fantastic thought experiment by Mark van Romstock.
What did he imagine?
He imagined two separate but highly entangled boundary regions. Let's call them left and right. Because they're maximally entangled, the RT formula guarantees they must be connected in the bulk. There's a smooth, traversable wormhole between them.
An Einstein-Rosen bridge.
That's it. Now, what happens if you start to systematically reduce the entanglement between left and right?
Well, the formula says the area of that minimal surface, the wormhole throat, has to shrink.
It has to shrink. The geometric connection is literally held together by the quantum correlations. As the entanglement goes to zero, the wormhole throat gets narrower and narrower.
And when the entanglement is completely gone,
The wormhole pinches off entirely. The two space-time regions disconnect. They become separate universes.
so the classical connectivity, the simple fact that I can travel from point A to point B, is not fundamental. It is actively being sustained by quantum entanglement.
If the glue vanishes, the fabric of space literally fragments.
That's mind-blowing.
It led Maldacena and Susskind to formalize this into the EPR conjecture.
Entanglement, EPR, is the same thing as a wormhole.
ER. They are two descriptions of the same physical reality.
Are you seriously suggesting that every pair of entangled particles in the universe is connected by a tiny, microscopic wormhole?
That is precisely the suggestion. Our smooth macroscopic space-time is just the statistical average of a buzzing, frothing foam of trillions upon trillions of these microscopic wormholes linking everything that's entangled.
Wow.
Entanglement isn't just a weird correlation, it's the physical bridge.
We've got the what entanglement builds space. Now, how does it actually work? What is the architecture of the projector?
To get from the discrete quantum bits on the boundary to the smooth curved geometry of the bulk, physicists turned to computational models, specifically tensor networks.
And the particular one that works is MIRA, the multi-scale entanglement renormalization ansatz, which is a bit of a mouthful.
It is, but at its heart, it's basically a data compression algorithm.
But a very specific one.
A very specific one. Because when you take a quantum state and model it using this mirror network, and then you draw a picture of the network, the geometry it naturally creates is identical to the hyperbolic geometry of ADS space.
Let's use an analogy, like compressing a high-resolution photo into a thumbnail.
That's a great analogy. So imagine you have a long row of pixels at the bottom. Those are your qubits on the boundary. High energy, high detail.
The original image.
Right. To compress it, the MRA algorithm groups those pixels into blocks, processes them, and creates a new, smaller, lower resolution layer just above it.
That's the renormalization step. You're coarse graining the data.
Exactly. And you just repeat that process. You build layer upon layer, and with each layer, the resolution gets coarser, the energy scale drops.
And that vertical direction, the direction that tracks the level of compression.
That becomes the emergent radial dimension of the bulk spacetime. The Mary network just naturally builds the right curvature for ADS space, simply by optimizing the entanglement structure of the data.
So our universe, the bulk, is literally a picture of the most efficient quantum data compression algorithm running on the boundary.
This is the ultimate expression of John Wheeler's It from Quibbit. Geometry is just a visualization of data processing.
And the shortest paths through the bulk that light travels on, geodesics.
They map directly to the most efficient information channels through the MRA network. The quickest way from A to B is the path of least computational resistance.
But this beautiful picture has a serious problem, a paradox about location, the bulk locality paradox.
Right. The paradox is this. If you have one specific local particle sitting right in the middle of the 5D bulk,
Okay.
the dictionary says its information must be spread out, non-locally, all across the 4D boundary. So if you can access that particle's information from boundary region A, and also from a totally separate boundary region B.
Haven't you just violated the no-cloning theorem of quantum mechanics?
Exactly. The no-cloning theorem says you can't make a perfect copy of an unknown quantum state. If A and B both have the full information, you've cloned it. It was a huge puzzle.
And the solution came from computer science.
It did. Physicists realized around 2015 that ADS-CFT must be functioning as a highly redundant quantum error-correcting code, a QECC.
Our reality is protected like critical data on a hard drive.
That's it exactly. Think of it like a sophisticated secret sharing scheme. The particle in the bulk is the logical qubit, the secret.
And that secret isn't stored in any one place.
No, it's encoded into the global entanglement structure of thousands of physical qubits on the boundary.
So how does the error correction work?
It's redundant. If you look at any single physical qubit on the boundary, You find zero information about the bulk particle. It just looks like random noise.
The information is hidden in the correlations.
It's only recoverable when you look at the correlations between a large enough fraction of the boundary qubits. You need to access, say, more than half of the boundary to decode the secret.
So if a small part of the boundary gets destroyed or lost,
the rest of the entangled system still holds enough information to perfectly reconstruct the original bulk particle. The information is safe.
this is the key to the stability and solidity of our experience.
It has to be. Why doesn't the table in front of you just flicker and dissolve from quantum noise? Because space-time is actively protecting itself against those errors.
The reality we see lives in a protected subspace of the holographic code.
So that smooth local reality is maintained, despite this furiously noisy, non-local quantum computation happening underneath it all.
The reliability of the universe is a feature of its own architecture. It's built to be self-healing.
But we have to confront the fact that this beautiful, successful model describes an idealized universe in a bottle.
The bottle being anti-de Sitter space, negatively curved with that reflective boundary.
Well, that's not our universe.
No, it's not. Our universe is expanding and it's accelerating. It has a positive cosmological constant. We live in what's called de Sitter, or DS, space.
And that geometry makes the holographic principle much harder to apply.
It does. A lot of it comes down to where you put the screen. Where is the boundary of our universe?
In the ADS model, the boundary is at spatial infinity. It's a time-like surface. It exists alongside the bulk for all of time.
It's a stable canvas to project onto.
But in our expanding de Sitter universe, where everything is accelerating away from everything else, the effective boundary becomes the cosmological horizon, or what we call future infinity. It's a space-like surface. It's located at the end of time.
And that creates a huge problem, the teleological paradox.
Right. If the information that defines the present moment is located on a boundary in the infinite future.
Does the future project the past? Are the dynamics of reality determined by the final state of the universe?
It creates enormous problems with causality. The math just isn't as clean or rigorous as it is for the stable IDS case. So this has pushed physicists to look for other approaches.
Which brings us to the cutting-edge celestial holography.
This is the attempt to define a holographic dual not for a cursed universe, but for flat space Minkowski space, which is a really good approximation of our universe locally.
And what's the screen in this model?
The screen is the celestial sphere.
You mean the night sky?
Literally the sphere of the night sky, as seen at null infinity. That's the place where all light rays eventually end up after traveling forever.
So the screen isn't a wall. It's the information encoded in all the light that has reached the asymptotic edge of space-time.
Exactly. And the math is incredibly suggestive. Researchers like Andrew Strominger found that the fundamental symmetries of gravity in flat space,
which are very complicated,
part of something called the BMS group. They found that those symmetries mathematically match the symmetries of a two-dimensional conformal field theory living on that celestial sphere.
So the dance of gravity and particles here in our 4D world is secretly encoded in the correlation functions of a 2D celestial CFT living on the sky.
The implication is just stunning. The hologram is the data recorded in the light at the edge of the universe. Every particle collision, every scattering event leaves its mark there, creating this vast 2D computation that generates the 4D bulk we experience.
Okay, we've dealt with space being an illusion woven from entanglement and gravity being a thermodynamic byproduct, but space and time are fundamentally linked. So if space is emergent, time must be too.
The problem of time is maybe the deepest mystery in all of quantum gravity. When you try to write down the fundamental equation for the quantum state of the whole universe.
The Wheeler-DeWitt equation.
Yes. It famously gives you a static, non-evolving state. H pi psi equals 0. The universe, in that formal sense, just is. It doesn't evolve.
Which suggests time isn't an external clock ticking away. It's some internal parameter that we're misinterpreting as flow.
And in the holographic context, we can start to see how that might work. We view time thermodynamically.
So evolution in the bulk things moving, stars burning, us talking, corresponds to what on the boundary?
It corresponds to the process of thermalization. The quantum information on the boundary is spreading out, becoming more complex, more scrambled.
The arrow of time is just the arrow of increasing entanglement complexity. Time flows because the underlying quantum state is getting messier.
Leonard Susskind formalized this with another duality, a companion to the area law. If entanglement equals area.
He proposed complexity equals volume.
Complexity equals volume. And this was needed to explain a weird feature of black holes.
What was that?
Well, after a black hole forms, its event horizon area stabilizes pretty quickly. It reaches maximum entropy. It's in equilibrium.
Okay.
And yet, the volume of the interior of the black hole, or the wormhole connecting to them, it keeps growing. And it grows for an exponentially long time, far longer than the lifetime of the black hole itself.
Why does the inside keep growing if nothing new is falling in and the surface area is fixed?
Susskind's argument is that this geometric growth corresponds precisely to the quantum computational complexity of the boundary state.
A what now?
It's a measure of the minimum number of simple logic gates, or computational steps, you would need to build that quantum state from some simple starting point.
So the geometric expansion of the black hole's interior is a physical manifestation of its own ongoing computation.
The universe is constantly calculating. And the expansion of the black hole interior, maybe the expansion of our own universe, is a geometric picture of the growing computational complexity of the underlying quantum system.
Gravity and geometry are the visual interface of a giant, constant computation.
That's the idea.
We started this by questioning the idea of volume. And we've ended up with a universe that seems less like a physical stage and more like a computation.
The classical intuition that guided physics for centuries has been completely dismantled step by step.
And the ontological implications are just staggering. Spacetime isn't fundamental. It's a network of information woven from entanglement.
Gravity isn't a primary force. It's the thermodynamics of that information. And we and everything around us are complex excitations of a highly redundant, two-dimensional quantum code.
The word hologram feels too static, too passive for this.
It is. The universe is dynamic, it's self-healing, it's computational. Our perceived reality, the smooth depth, the pull of gravity, the flow of time, that's just the user interface.
It's like the icons on a desktop hiding the furious processing of zeros and ones happening underneath.
A great way to put it. The universe isn't in space. Space is in the quantum state.
So as we look up at the night sky, at that celestial sphere, we could literally be looking at the hard drive of reality, observing the scattered data from this massive computation that's generating our world.
And that raises one last profound question for you to think about.
What's that?
If the perceived solidity and locality of our universe, the simple fact that a particle can be right there, is being maintained and protected by a robust quantum error-correcting code, what does that imply about our ability to ever access the fundamental reality? If space is built to correct errors, to protect its underlying structure from being disturbed, is the raw code of the universe fundamentally inaccessible to those of us who live inside its protected interface?